Since time immemorial, humans have looked up to the skies and the heavens, attributing to their mysterious properties in our quest to discover the unknown. Over the past decades, our eyes were set on one particular heavenly body, Mars. This universal and enduring need to understand the universe is closer to being quenched than ever. We have discovered new worlds and pushed the limits of our scientific and technological knowledge. And while we have strived to learn more about the universe, our first stepping stone into the cosmos is Mars, where its relative closeness leads to the possibility of setting the foundation for human deep space exploration and making our species multiplanetary. We are UC Mars, and we invite you on our journey to the Red Planet. The ultimate goal is to set a foundation for a human colony on Mars in 2040. To undergo this monumental task of traveling to a new planet and becoming a multiplanetary species, our scientific group tackled the problems of traveling to the Red Planet, delving into space travel, the parameters of the rocket, and the trajectory to Mars, while adhering to our ultimate vision. Space travel is exciting, but where could we go? What places in space are there to visit and explore? Within our solar system, after the Earth, Mars is the best candidate for an habitable planet for several reasons. Its soil may contain water to extract, it isn't too cold or too hot, ranging from minus 150 degrees to 20 degrees. There is enough sunlight to use solar panels. Gravity on Mars is roughly 38% that of our Earth's, which is believed by many to be sufficient for the human body to adapt to. It has an atmosphere, although a thin one, that offers protection from cosmic radiation. The day-night rhythm is very similar to ours here on Earth. A Mars day is 24 hours and 39 minutes. This means that Mars is obviously our first goal, but what is next? In order to understand space travel, one first needs to understand the speed of light. It is the ultimate speed in our universe, and it travels at 300,000 kilometers per second. That means light is able to go around the equator 7.5 times in 1 second. This may seem like a lot, and on a human scale, it is. But on a scale of our universe, it is not enough to shorten the huge distances to other solar systems. The closest star system to ours is Alpha Centauri, which is 4.5 light years away. That means that, even if we were able to reach the speed of light, it would take us 4.5 years to get there. Moreover, there is a tremendous amount of energy needed to accelerate objects even close to the speed of light. The fastest man-made object is a probe, the Helios 2, that reached the top speed of 72 kilometers per second. That is 0.02% the speed of light. If we were to send this probe to Alpha Centauri, our closest neighboring star, it would take 18,000 years to arrive. That is 670 human generations, or the amount of time elapsed since the last ice age. Imagine that the furthest star ever noticed by our instruments lies 9 billion light years away from Earth. That is 2 billion times more than Alpha Centauri. With our current technologies, we are far away from reaching speeds that will take us anywhere outside our solar system. Therefore, Mars is the first step needed in our long journey to explore the cosmos. The types of propulsion that are used in space travel can be divided into two categories: chemical and electromagnetic propulsion. Electromagnetic propulsion allows really high speeds, but constrains the maximum weight of the rocket to a few hundred kilograms, while chemical propulsion, the most commonly used, allows for a heavier rocket but far slower speeds. Because of the absolute vacuum in space, an oxidizer is needed for the fuel to combust. Our company decided to invest in using methane as rocket fuel and liquid oxygen as an oxidizer. Methane allows for lighter and less complex tanks than hydrogen. It does not need to be kept at such low temperatures and is less susceptible to temperature and pressure changes. Nearly half the mass of the lunar crust consists of oxygen. Therefore, having a base on the moon in which oxygen is extracted will be extremely cost efficient in multiple ways. Less oxidizer fuel would need to be brought from Earth, critically lowering the weight of the initial payload and thus radically reducing launch costs. The absence of atmosphere on the moon also means less air resistance on the rocket, resulting in less fuel needed to depart after the rocket is refueled. Another option for a space base is the use of Lagrange points. These are points in space that every two-body system in space has, like the Sun and the Earth, and like the Earth and the Moon. There are 5 positions in an orbital configuration of 2 large bodies wherein an object will maintain its position relative to them. Building a space station in L1 or L2 for refueling options decreases launching costs and total energy usage dramatically. Abiding to our vision and goals, the rocket ship is an important part of the mission to get to Mars. The parameters set to guarantee the success of the mission start with the design of the rocket. In coordination with the other groups, it became abundantly clear that 2 rockets were needed in order to send supplies first, and on the second trip, 2 years later, the crew. To set a foundation of human civilization on a new planet is no mean feat, and a rocket needed to be up to the task. A rocket ship capable of carrying up the payload of food and the habitat materials was needed. Looking at available commercial rockets, it becomes evident that the big Falcon rocket from SpaceX would make the best candidate. Its large size and Raptor engines would allow for a payload capacity of 150,000 kilograms to be taken to Mars, and its possible refueling ability on Mars makes it the most efficient and cheapest rocket to get us to the Red Planet. The reusability of the rocket, with using methane endemic to Mars, would not only slash costs, but also prevent a graveyard of unusable rockets on the planet. The 2 rockets used will be the BFR Cargo, which will take all the necessary supplies to Mars, before the BFR Crew rocket takes the voyage. Every 2 years, there is a window for a journey to Mars, in which Mars and the Earth are properly aligned for a trip, which take the least amount of energy. The trajectory that the rocket has to take is a parabolic curve. This curve is exactly half an ellipse and is called the Hoffman trajectory. This path minimizes the amount of energy required to complete a voyage. Arriving earlier or later will require an increased amount of total energy. For the Earth-Mars system, the spacecraft must set off 96 days ahead of opposition and will reach Mars about 163 days after it. The spacecraft will depart the gravitational field of Earth with a hyperbolic access speed of 3 km per second, and after the cruise, it will enter the sphere of influence of Mars with a hyperbolic access speed of 2.5 km per second. Lastly, we need to remember that if humans didn't always want to satisfy their innate urge to see what's out there, technological and human progress would stagnate. It is in human nature to discover and explore our surroundings. Space is just the next and inevitable step towards learning more about the world and providing future generations with a new home. The possibilities are endless when we look to the heavens.